The European Space Agency just published the largest, sharpest map of the universe ever assembled, a single data release containing tens of millions of galaxies, photographed in exquisite detail. And when cosmologists finished adding up everything visible in that map, roughly 95% of the universe still was not there. The stars, the galaxies, the gas, the dust, everything that actually shows up in the pictures accounts for about 5% of what the universe weighs. The rest is missing. And this new map was built specifically to hunt it. Nobody expected the most beautiful astronomical images of the decade to double as evidence in the biggest unsolved accounting problem in science. Stick around, because I'm about to walk you through what Euclid's new data release actually shows and what it strangely refuses to show. And hit subscribe now, because this channel covers real space discoveries without the exaggeration, and this story is only getting stranger as the data piles up. Let's go back to where this story actually begins, with a woman counting smudges on glass photographic plates. In the late 1960s, at telescopes in Arizona, an astronomer named Vera Rubin was doing some of the least glamorous work in science. Night after night, she and her colleague, Kent Ford, aimed a spectrograph at the Andromeda Galaxy and measured how fast its stars were moving, one small patch at a time. The work was slow and repetitive, long exposures in a cold dome, then days of squinting at faint smears on glass plates, converting them into numbers by hand. Rubin liked it that way. She had picked a quiet corner of astronomy, partly because she was one of very few women in the field and had spent her career being pushed away from the fashionable problems. Galaxy rotation was supposed to be safe, settled, boring science. It was not. The rule Rubin expected to confirm was the same one that governs our solar system. The farther you are from the center of mass, the slower you should orbit. Mercury tears around the sun while distant Neptune crawls. The stars at a galaxy's bright center should whip around quickly, and the stars at the faint outer edge should drift lazily. That is what gravity demands, if the visible stuff is all there is. But when Rubin and Ford plotted their measurements, the curve refused to droop. The stars at the far edges of Andromeda were moving just as fast as the ones deep inside. Galaxy after galaxy showed the same impossible pattern. It is a result you can explain in one sentence, and it has haunted physics ever since. Either our law of gravity breaks down at galactic scales, or every galaxy is embedded in an enormous halo of invisible matter, far more massive than everything we can see, holding those speeding outer stars in their orbits. A story from those years tells you everything about the odds she was working against. When Rubin became one of the first women officially allowed to observe at the Great Palomar Observatory, she discovered the facility had no women's restroom. Her response was to cut a little paper skirt and stick it onto the stick figure on the men's room door. Problem solved, she said, and went back to work. That is the person who found the strongest evidence for the biggest missing mass problem in the history of science patiently at unfashionable telescopes, while much of her field looked elsewhere. Rubin was not even the first to smell the problem. Back in 1933, a famously combative Swiss astronomer named Fritz Zwicky had measured galaxies whizzing around inside the Coma cluster and calculated that the cluster should fly apart unless it contained vastly more mass than its light suggested. He called the missing stuff dark matter, and his colleagues largely ignored him for 40 years. Rubin's rotation curves made the problem impossible to ignore. By the 1980s, most astronomers had accepted something deeply uncomfortable. The universe we can see is a thin frosting on a cake we cannot. Then, in the late 1990s, it got worse. Two rival teams of astronomers were using distant exploding stars as mile markers to measure how much the expansion of the universe was slowing down, as everyone assumed it must be, since gravity should be pulling the cosmos back together. The technique relied on a particular kind of stellar explosion that always detonates with nearly the same intrinsic brightness, which makes each one a standard candle. Measure how faint it looks, and you know how far away it is. Measure how its light is stretched, and you know how much the universe has expanded since the explosion. The two teams raced each other for years, checking and rechecking, each fully expecting to announce the rate at which cosmic expansion was coasting to a stop. Both teams found the opposite. The expansion is speeding up. Something is actively pushing the universe apart, overwhelming gravity itself on the largest scales, and nobody knows what it is. It was given the placeholder name dark energy. The discovery earned a Nobel Prize, and here is the tally it left us with. Dark energy appears to make up roughly 68% of the universe. Dark matter, roughly 27%. And everything humanity has ever seen, every star, every planet, every galaxy, every atom in your body, is squeezed into the remaining 5% or so. It is worth pausing on how strange our situation actually is. We have precise measurements of how much of the universe is missing, and almost no idea what the missing part is, and it is not for lack of trying. For decades, physicists have proposed candidate after candidate for dark matter. Heavy, shy particles that barely interact with normal matter. Ultralight particles so ghostly that they behave more like waves than objects. even black holes left over from the first moments of creation. To catch the heavy candidates, they buried exquisitely sensitive detectors deep in mines and under mountains, tanks of liquid xenon shielded from every stray cosmic ray, waiting years for a single telltale flicker of a dark matter particle bumping into an atomic nucleus. The detectors kept getting bigger and more sensitive, and they kept measuring the same thing. Nothing. Each null result quietly killed off another family of theories. Physics has been living with that embarrassment for decades, and by now, there are really only two ways forward. Keep building bigger traps on Earth and hope, or map the invisible from space by watching what it does to the light of the visible, and let the universe itself tell you how the missing stuff behaves. That second path has a catch, though, and the catch is scale. Dark matter does not glow, so you can only detect it statistically, through a subtle trick of gravity we will get to in a moment, and the signal is so faint that you need exquisitely sharp shapes for not millions, but billions of galaxies spread across a huge fraction of the entire sky. Ground-based telescopes struggle because Earth's atmosphere smears every image, and the smearing itself mimics the signal you're hunting. Hubble has the sharpness, but its view is a pinhole. Photographing a third of the sky with Hubble would take something like 1,000 years. What cosmology needed was a contradiction in hardware, a telescope with space sharpness and a survey machine's appetite. That is exactly what Euclid was built to be. The European Space Agency spent 2 decades and roughly 1.4 billion euros designing it, named it after the ancient Greek father of geometry, and launched it in July of 2023 from Cape Canaveral, riding a SpaceX rocket because Europe's own launchers were unavailable at the time. It now flies about 1 million miles from Earth, parked near a gravitational balance point called the second Lagrange point, in the same neighborhood as the James Webb Space Telescope. Here is what makes Euclid fundamentally different from Webb, because people constantly mix them up. Webb is a keyhole instrument. It stares at tiny patches of sky with overwhelming depth. Euclid is a panorama machine. Its mirror is modest, about 4 feet across, but its 2 cameras are enormous. The visible light camera captures images with roughly 600 million pixels, and each single exposure covers more sky than 2 full moons. Alongside it sits a near-infrared instrument that measures the colors and distances of galaxies by the tens of thousands per exposure, splitting their faint light into spectra so that each galaxy's redshift, the stretching of its light by cosmic expansion, becomes a measured distance rather than a guess. That second instrument is what turns a flat photograph into a 3-dimensional atlas. And by the end of the survey, it is expected to have measured precise distances to tens of millions of galaxies, a spectroscopic haul that dwarfs anything previously attempted from space. Over 6 years, Euclid is mapping more than a third of the entire sky, with a plan to capture useful shapes and positions for on the order of 1.5 billion galaxies, reaching light that has traveled up to 10 billion years to get here. Webb reads single pages under a microscope. Euclid is scanning the whole library. If you're finding this valuable so far, do me a quick favor and tap the like button. It costs you nothing. It tells the algorithm this kind of no-hype space coverage is worth showing people, and it genuinely helps the channel keep making these. So how do you photograph something invisible? This is the first thing the new data release delivers at full scale, and the method deserves a proper explanation, because it sounds like magic, and it is actually just geometry. Einstein showed that mass bends space, and bent space bends light. When the light from a distant galaxy passes through a region thick with dark matter on its way to us, the galaxy's image gets subtly stretched and sheared, the way the world warps when you look through the base of a wine glass, or through an old, slightly rippled window pane. For almost every individual galaxy, the distortion is hopelessly small, a fraction of a percent change in shape, but distortions caused by the same invisible clump all lean in a coordinated way. Measure the shapes of enough galaxies, millions upon millions of them, and the pattern of invisible mass between you and them emerges out of pure statistics, like a fingerprint developing on glass. Euclid's first releases proved the machine works even better than its designers hoped. The debut images alone made front pages worldwide. A single early portrait of the Perseus galaxy cluster captured 1,000 cluster galaxies in one frame, with more than 100,000 fainter galaxies scattered in the background behind them, each one a smudge of ancient light containing billions of stars. Researchers pointed out something delightful about that image. The Perseus cluster is one of the most massive structures in the known universe, and it is itself held together by dark matter, which means the very first showpiece image this dark universe detective ever took was, fittingly, a portrait of a crime scene. The bright galaxies in that frame simply do not have enough combined gravity to stay bound together. Something invisible, outweighing them several times over, is holding the whole city of galaxies in place. And in the first big catalog drop, covering just 1 week's worth of deep observing across 3 patches of sky, Euclid delivered detailed imaging of about 26 million galaxies. 26 million from a week. Astronomers who had spent entire careers assembling catalogs of a few thousand galaxies suddenly had to reckon with a fire hose. The full data release now takes that fire hose and opens the valve the rest of the way, expanding the mapped area enormously and stacking the deep fields to their intended depth, which is precisely why cosmologists have been circling this date on their calendars for years. To give you a sense of the scale of imaging we are talking about, the mission team at one point stitched a stretch of the survey into a single mosaic containing more than 200 billion pixels, covering an area of sky hundreds of times larger than the full moon, and that mosaic represented about 1% of the finished survey. 1%. Viewers online spent hours just zooming into it, diving from a wide field sprinkled with thousands of galaxies down and down until a single anonymous spiral filled the screen. A galaxy no human had ever examined before, one of millions in the frame, each fully resolved. The mission produces on the order of 100 gigabytes of compressed data every single day, so much that ESA had to build a dedicated ground system of data centers across Europe just to digest it. Astronomers now say, without exaggeration, that Euclid will image more of the universe in its 6-year survey than every previous optical telescope in history combined. And buried inside those images, the telescope keeps finding gravity's party tricks, when a massive galaxy sits almost perfectly between us and a much more distant one. The foreground galaxy's gravity does not just smear the background light, it wraps it into a complete circle, a ghostly halo called an Einstein ring. They are genuinely rare, and Euclid keeps collecting them, including one hiding around a well-studied galaxy relatively close to home that an ESA scientist first noticed in blurry test images taken while the telescope was still being focused. The early catalogs also flagged roughly 500 candidate gravitational lenses, spotted by pattern-hunting software that had been trained with the help of citizen volunteers who classified galaxy images by eye. That partnership deserves a highlight of its own because it is quietly one of the most human things about this very industrial mission. Tens of thousands of ordinary people, through an online galaxy classifying project that has been running for years, taught the mission's artificial intelligence what spiral arms look like, what a merger in progress looks like, what a suspicious ring of stretched light looks like. The machine then applied those human-trained eyes to millions of galaxies at a speed no army of volunteers could match. Each lens it finds is a free, natural telescope, and each one is also a scale, because the size of the distortion weighs the invisible matter doing the bending. Astronomers expect the finished survey to multiply the number of known strong lenses by an enormous factor, turning what was once a career-defining rarity into a daily occurrence. Which brings us to the second discovery layer in this release, and it is quieter than the pretty pictures, but honestly stranger once you sit with it. When researchers stitch Euclid's shape measurements together, what comes out is a map of the dark matter itself. The first time humanity has charted the invisible skeleton of the universe across such a large volume at this sharpness. And the skeleton has a shape. Dark matter is not spread smoothly. It gathers into a vast three-dimensional web, dense knots where clusters of galaxies live, long filaments strung between them like spider silk, and huge voids in between where almost nothing exists at all. The galaxies we see are essentially fairy lights, strung along invisible cables. Our own galaxy sits on one of those cables. Everything you have ever seen in the night sky is decoration on a structure that has never once been directly observed. And the map has a time axis, which is the part researchers get most excited about. Because light takes time to travel, Euclid's deepest galaxies are also its oldest, so the survey can slice the universe into layers by distance, like the growth rings of a tree. The near layers show the cosmic web as it is now. The far layers show it as it was billions of years ago, younger, smoother, still knitting itself together. Comparing the layers turns a photograph into a time lapse of creation. You can literally watch, statistically, how fast gravity has been winning its long war against expansion, pulling matter into knots and filaments while dark energy stretches the space between them. That growth rate is one of the most information-rich numbers in all of physics, because both dark matter and dark energy leave their fingerprints on it, one by pulling structure together, the other by slowing that pull down. Here's the detail that tends to stop people in their tracks, though. And when cosmologists measure how clumpy that web is, the answer comes out slightly wrong. The standard model of cosmology takes the universe's baby picture, the afterglow of the Big Bang, and runs gravity forward 14 billion years to predict exactly how lumpy the cosmic web should be today. Weak lensing surveys on the ground kept finding a universe that is a few percent smoother than that prediction, structure that seems to have grown a little more slowly than it should have. The discrepancy even has a name among cosmologists, a tension in the clumpiness parameter. A few percent sounds like nothing, but the prediction machinery is so precise that it is not supposed to miss by that much. Researchers remain genuinely divided about it. It could be a subtle measurement bias that the ground-based surveys share, or it could be the first visible crack in our model of how the dark universe behaves. Euclid was built, in large part, to settle exactly this question, because from space above the atmosphere, the shape measurements are cleaner than anything that came before. That is what makes this data release different from just another photo album. It is a referee stepping onto the field. And the funding story deserves a moment of honesty here, because this kind of science does not simply happen. Euclid is a decades-long bet by European taxpayers, with contributions from NASA, and like every big mission, it has had its scares. Shortly after launch, the fine guidance system kept intermittently losing its guide stars, leaving the telescope unable to lock its gaze. And for a few weeks, the mission's core survey was genuinely at risk, until engineers rewrote the guidance software and uploaded the fix across 1 million miles. Then thin layers of water ice, just nanometers thick, began condensing on an internal mirror, quietly dimming the starlight, and the team had to choreograph delicate heating operations to boil the ice off without warping the optics. Both fixes worked, and the survey's efficiency actually came out ahead of the original plan. But it is worth remembering that every serene, perfect image in this release rides on top of engineers sweating over problems the public mostly never hears about, uploading software patches across 1 million miles of vacuum to a machine nobody can ever touch again. Now for the third finding, and this is the one that tends to unsettle people the most once they hear it explained properly, because it touches the fate of the universe itself. Everything I have described so far treats dark energy as a constant, a fixed property of empty space, the same yesterday, today, and forever. That assumption is baked so deeply into the standard model of cosmology that the model is literally named after it, the Greek letter lambda, Einstein's cosmological constant. If dark energy is constant, the universe's future is written. Expansion accelerates forever, galaxies recede beyond visibility, and the cosmos ends in a cold, lonely dilution. Grim, but at least predictable. Recently, though, a major ground-based survey that measures the positions of tens of millions of galaxies reported something that made cosmologists sit up very straight. Combined with other data, its measurements hint that dark energy may not be constant after all. The push may have been stronger in the past and may be weakening now. I want to label this carefully, the way the researchers themselves do. It is a hint, not a discovery. The statistical strength sits below the threshold physicists demand before claiming something this enormous, and hints of this size have evaporated before. But it helps to understand why even a hint causes this much commotion. If dark energy can change, then it is not a fixed property of space itself. It is something dynamic, a field, a substance, a process, something with an internal life that physics can actually study. And the universe's ending changes with it. If dark energy weakens toward zero, the runaway expansion calms into an endless, gentle coast. If it were ever to cross below zero, gravity eventually wins everything back, and the universe ends by collapsing in on itself in a reverse Big Bang. If instead it strengthened, expansion would one day tear apart galaxies, solar systems, and finally atoms. Nobody is claiming to know which of these is true. What is being claimed, cautiously, is that the first door to finding out may have just cracked open. But if it holds, it is hard to overstate what it means. A weakening dark energy would break the cosmological constant, rewrite the predicted fate of the universe, and hand physicists their first real clue about what dark energy actually is. And this is exactly the fight Euclid's full data release wades into. Euclid measures the growth of cosmic structure and the clustering of galaxies with a precision the ground surveys cannot match, using frozen ripples from the newborn universe, sound waves imprinted in the arrangement of galaxies as a ruler laid across 10 billion years. Over the coming analyses, this dataset will either calm the hint back down or harden it into the biggest result in physics in a generation. Either outcome is historic. That is not hype. That is simply where the measurement stands. While you're here, drop a comment and tell me which side you'd bet on. Boring, constant, or evolving dark energy, and what other space stories you want covered next. I read those comments, and they genuinely steer what this channel makes. Now, picture for just a moment what the night sky would look like if your eyes could see what Euclid is mapping. Step outside on a clear, moonless night. Instead of scattered stars on black velvet, the sky is dominated by a faint, colossal web, arcing from horizon to horizon, knots of pale mass connected by threads longer than anything you have a word for. And the familiar stars are just glitter caught in it. Every galaxy you can find with a telescope hangs at some junction of that web, like a droplet on a spider web at dawn. Somewhere in the middle distance, the web is gently, imperceptibly stretching, and the stretching is speeding up, and you would be looking, with your own eyes, at the two mysteries that make up 95% of everything. That sky is real. It is above you right now. You just cannot see it, and Euclid, in its patient statistical way, can. There is something quietly humbling about that. Human eyes evolved to spot ripe fruit and moving predators. A thin slice of light for a thin slice of survival. It took us until this decade to build an eye that can finally register the main structure of reality. And the first thing that I confirmed is that we have been admiring the frame and missing the painting. And Euclid will not be fighting alone. On a mountaintop in Chile, a giant new ground-based observatory named after Vera Rubin herself has begun photographing the entire southern sky every few nights. And its decade-long movie of the changing universe will interlock with Euclid's pin-sharp map, like two witnesses corroborating each other's testimony. The woman who was once denied a restroom at the world's great observatory now has a mountain, a telescope, and arguably the entire coming decade of cosmology named in her honor. Science moves slowly, but it does sometimes get things right. So what does all of this actually add up to? I think the honest summary is that Euclid has turned humanity's ignorance into a map. We still do not know what dark matter is. We still do not know what dark energy is, but for the first time, we know where the darkness is, how it is arranged, how it has grown over 10 billion years, and we have a fighting chance of catching it misbehaving. The full data release is not the end of that project. It is the first proper installment. The survey keeps running, the mapped fraction of the sky keeps climbing toward that final third, and each release will tighten the screws on every theory physicists have. Somewhere in the gap between 5% and 100%, there's at least one revolution in physics waiting, possibly two. And Euclid is not even the only machine currently drawing maps of everything. While Euclid charts billions of galaxies in visible and near-infrared light, a small NASA telescope has just finished photographing the entire sky, every direction, in 102 colors at once, building a completely different kind of all-sky map, one aimed at the origins of water and the first instant of cosmic time. What that little telescope found in its first full map deserves its own video, and it is coming to this channel. So subscribe and turn on notifications if you have not already, because the era of mapping the universe is just getting started, and there's a real chance the next data release adds another genuinely strange piece to this puzzle. Thanks for watching, and I will see you in the next one.